Hi, everybody. Hi, everybody. We're going to do section 2.1, which is all about limits. Let me share my screen with you. And here we go. And pow. So, intro to limits. So here we have a function. F of x is equal to x plus 2. And we want to know the limit as x approaches 2. Let me just pause. No, pause that. I don't want to pause. What we want to do, we want to find what's called the limit as x approaches 2 of f of x. And f of x is equal to x plus 2. So let's look what happens when x approaches 2. So if x is 1.9, f of x, which is y, is going to be 3.9 because it's 1.9 plus 2. By the way, we use y and f of x sort of interchangeably. But what about if x is equal to 1.9? Well, if x, oops, how did that happen? Let's take that back. Let's say if x is equal to 1.9, then y is going to be 3.99. If x is 1.999, y is 3.999, and so on and so forth. And here we go like that. If x is 1.999, then y is 3.99999. Now let's look at this from the other end. Let's look at this from the other end. Let's see what happens. Let's look at 2.1. I'm going reverse right now. I don't know if I should be doing it. Yeah. 2.1, 2.01, 2.001. See, what I'm doing here is first I was getting closer and closer. The x value is getting closer and closer and closer to 2. Now, from the lower side, now the x value is going to get closer and closer to 2 from the upper side, from the higher side, because 2.1 is pretty close to 2. 2.01 is a lot closer, and 2.001 is a lot closer, and 2.0001 is also a whole lot closer. So let's take a look here, and let's see. See our values here. Boing. Actually, let's make this a 1.12345, and let's make that 2.00001. Okay, so if you notice, as we get closer and closer and closer and closer to 2, coming from beneath the 2, the y value gets closer and closer and closer to 4. If I'm starting from 2.1 and going down and getting closer and closer and closer to x equals 2, then the y value gets closer and closer to y equals 4. Now, that's what limit means. Limit means that as I get close to x equals 2, the y value gets close to y equals 4. So we say that the limit as x approaches 2 is 4. Let me write that here. Say that actually I'm actually going to copy this here. I'm going to do what they call in ancient times, they call this a screen grab. And here we go. Screen. And copy that and put it right here. So we say that the limit as x approaches the limit of f of x, the limit of f of x as x approaches 2 is 4. So the limit is 4. We write this in a different way. I'll show you how we write it. We write it like this. We write it this way. The limit as x approaches 2. We draw a little arrow there. of f of x equals 4. And this is, of course, where in the case where f of x is equal to x plus 2. This is our case. So that all works. So it all works. Okay. I want to show you another idea here. So here we have, whoops, where to go? So here we have a situation where this is our function. So now we want to know the limit as x approaches -1. Well, you see, here's the thing. When x gets, as we see from the diagram, when x gets closer and closer and closer to -1 coming from down this side, when x gets closer and closer and closer to -1, the y gets closer and closer to 3. Even though there's an open circle here, which means the y value doesn't equal 3, but limit means I care about what's going to happen when y is closer to 3. So we're going to say that this is 3. Because now you see that little minus sign there? That does not mean -1. That means we're approaching our value from the negative side, from the dark side, from the lower side. So we say x approaches -1. So that first minus sign is for the number -1. But that minus sign up there almost looks like an exponent kind of in a way, or a superscript, if you will. That means we're approaching from the negative side. It means we're approaching from the negative x values. And the second line is saying the limit as x approaches -1, and that little plus sign means the limit as x approaches -1 from the positive direction. It means if I'm coming in from down from the positive x values, 5, 4, 3, 2, 1, 0, and we're getting and x is getting closer and closer to -1. Well, the y values, if you notice, are getting closer and closer and closer to 2, not to 3, but to 2. There you go. And finally, what about if we say the limit is x approaches -1, and I don't have a plus or a minus? What is that? What is that? Well, the answer is does not exist, because the answer is it does not exist, because if the left side doesn't match the right side, there's no overall limit. Because if I just say, well, what is the value? What does the y value get close to as x gets close to -1? Well, it's hard. I can't answer that question because on one side it gets close to 3, and the other side it gets close to 2. There's no unified answer. So therefore, I have to say the limit does not exist. D&E does not exist. Now the next question is, what is find f of -1? Now f of -1 is going to be that dot, that little dot right there, saying that when x is equal to -1, y is equal to -1. Now, that is the story with that. And now I'm just going to let's just check now we check the answer, and there we go. So it all works out beautifully, and that's what we talk about limits now. That's what we mean with limits. So now we're looking at a new example. Now I just want to point out that in the example we just did a second ago, and the current example we're about to work on, is a fundamental difference in just that up here we were working with an equation. We were working with the equation y equals x plus 2. And based on that equation, I was able to calculate values. I was able to crunch in values on a spreadsheet and get more definitive answers. Whereas here, we're not working with we don't really know what the equation of this graph is, of this curve. We see we have a nice curve. We don't know the equation of it per se. We were not given any equation, and wouldn't even begin to, I wouldn't even presume to say what it is just based on a picture. And but it doesn't matter as far as the question that we're trying to answer is concerned. We're trying to say, what is the limit as x approaches 2 from the negative direction? Well, as x approaches 2 from the negative direction, I'm coming down from the negative side. I'm getting closer and closer and closer to 2. Y is getting up to over 2, close to 3. And as I get closer and closer, y, as I get closer and closer to to x to 2 from the negative side, the y gets closer and closer to 3. So I'm going to put a 3 over here. And as far as coming from the positive side, again, when x gets closer and closer to 2 from the positive side, y gets closer and closer also to 3. Now, what is the overall limit? Can there be an overall limit? I mean, there's a big gaping circle there. Can there even be an overall limit? And the answer is yes, because as long as the values match, as long as the left and the right match up, then we have an overall limit. And finally, but what is f of 2? Well, f of 2, if x equals 2, y equals 2. F of 2 equals 2. So even though this function has a nice big gaping hole there, it's it's still there. We still can talk about a limit, and that's really the beauty of calculus, because in calculus, let me just check the answer. And there you go. And I love this program, My Open Math. It's part of our curriculum. Our homework is in this program, and it's wonderful because again, it has so much. It gives you so much help. It has, first of all, besides the fact you have my fabulous videos, which I'm making right now. You also have My Open Lab has other videos to explain everything, and we have the textbook. We have all kinds of wonderful features in My Open Math Lab. So this is. I want to point out that when x approaches 1, let's look at x approaches 1. When x comes in from the negative side, we see that the y values get close to 4. When x comes in from the positive side, the y values get close to 1. So the left and the right don't match each other. But what about when x equals 1? Where's the black? Where's my solid dot? Well, there is no solid dot. It doesn't necessarily have to be. You could have a function which is just not defined at the value of x equals 1. That happens sometimes. On the other hand, if I look when x equals 4, when x approaches 4 from the negative side, y approaches 1 right there. When x approaches 4 from the positive side, y approaches 3 right there. But the value of y when x equals 4 is 5. So again, there's no overall limit, and there is a value, and the value is this right here. So let me just let's actually just that's so they're asking us here, what is the overall limit when x approaches 4? And the answer is DNE, does not exist. Because if the left and the right don't match, then the limit does not exist. What about approaching 0 from the negative direction? Well, when I approach 0 from the negative direction, the y value gets close to 3. So I'm just going to put a 3. Very nice. And what about when I approach 5 from the positive direction? When I approach 5 from the positive direction, I get the y value is equal to 2, or I should say not equal to, it becomes close to 2. All I care about, I don't care what happens when x equals 5. I care about when x gets close to 5. And that's really the wonderful thing about calculus, is that we may not know what's happening at that particular point, but we know the what happens as you get closer to that point. So how about the limit as x approaches 1 of f of x? Now, like I said, x equals 1, as we could see, there's an open circle here, there's an open circle there, there's no individual dot anywhere. So x equals 1 is really not even in the domain of the function. It's really not defined for this function. But that's the beauty of calculus. Even though the value at x equals 1 is undefined, or is out of the domain, I should say, it's not part of the domain, even though there is no value, even though there is no y value when x equals positive 1, nonetheless, there is a limit. And the limit, oh, well, in this case, there is no limit because the left and the right don't match. But if I would ask for the left-sided limit, or the negative limit, negative-sided limit, that would be 4. The positive-sided limit would be 1. See, I'm looking at 1 right there. And that's what I would write. The overall limit doesn't exist, and that's for D and E. And let me just oops, I'm sorry. Whoopsies. f of 4 equals 5. I'm sorry, I don't know why I wrote that. I guess I thought it said limit for a second. I had a moment. What did I say? The answer is just 5. And I'll explain that in a second. Just type it in. The answer is 5. And we're all good. F of 4, not a limit, but f of 4. When x equals 4, y is that red dot right there, 5. So that's why that's a 5. Thank you for that. Now, in the same example, what is the limit as x approaches 3? What is the value of f of 3? Well, value of f of 3 is 2. I'm going to put 2 right there. And what is the value? What about the limit as x approaches 3 from the negative direction? Well, as x comes in from the negative direction, the y value gets closer and closer to positive 3. Not that f of 3 equals 3. It doesn't. F of 3 actually equals 2. But we're talking about limits now. The limit as it approaches 3 from the negative direction is positive 3. And the limit as it approaches from the positive direction, well, as it gets closer and closer from the positive side, then the y value gets closer and closer to 2. And the fact that the y value actually equals 2 when I hit 3, that's wonderful, but that's really not even the point of a limit. Well, let's get to what the point of a limit is. The point of a limit is that the point of a limit is that sometimes a function may not have a value at a given point. So when x equals 1, it may not have a value. Over here, when x equals 7, there's no y value. But even though there's no actual y value, we could learn a lot about the function by seeing what happens when x gets close to y, gets close to the value 7. So when x is close to 7, we see that the y value on both directions gets closer and closer to y equals 6. So therefore, I can write that the limit. Therefore, I'm going to write that the limit as, let me just copy it this way. The limit as x approaches 7 equals 6. Now notice that I didn't write a plus or a minus after the 7. I just wrote 7. That means the overall limit, and the overall limit exists if the negative side and the positive side have the same value, which in this case they do. They all have x. I don't know if you can see it. They all have y equals 6. Y it gets closer to the y value is closer to 6 as the x value gets closer to 7. So even though the function is not defined, and that's a beautiful thing, because there's a lot of functions where a certain value is not defined, but we can still talk about a limit. That's really that's the thing where I personally find the coolest about calculus, meaning that the value may not exist, but who cares? So what? So it doesn't exist. That's all right. We'll still figure it out. We'll still figure it out as much as we can, or, as much as we can possibly figure out. And sometimes it's amazing how much you learn from just seeing what happens to a function as they get close to a value, even though value at that point that I'm getting close to may not even exist, or who knows what. And that's the beauty. I feel that's the beauty of limits and functions. Here's a wonderful example. The limit as x approaches -1 of 7x squared minus 6x. Now, for a problem like this, sometimes it's just super simple. Just take this value -1, and just plug it into the equation and see what happens. Plug it into the formula, if you will. And as we're going to learn, when the formula in question that we're taking the limit of, when it's a polynomial, all you got to do is just plug in that value. So this is going to equal 7 times -1. You know what I'm going to do? Let me just. This is going to be equal to 7 times -1 squared. minus 6 times -1. There we go. And that is equal to 7 plus 6. 7 plus 6. And that equals lucky 13. Why is it plus 6? Because the negative and the negative cancel. Why is it positive 7? Because the negative 1 squared gives me positive 1, so just 7 times 1 plus 6, 7 plus 6, 13. And that is the answer. And actually, that's actually a question right here. I didn't make that question up. The question is right here. I'm going to just type that in, and there we go. There's our answer. Isn't that nice? It's a great feeling when you get the right answer. Okay, now here's let me just copy this here. And we'll take copy this here. Play with this. Okay, we're going to evaluate this limit here. So let's okay. So we want to evaluate this. Now here's the thing. If I would just plug in x equals 9, I would get 9 minus 9 on the bottom of the fraction. And let's just do it actually. Let's just do it. I would get 9 squared minus 14, oops, minus 14 times 9 plus 45. That is equal to, let's see, 14 times 9. Let's go to a little calculator here. So it's 81, 80, plus 45 plus 45, then minus 14 times, and that is equal to, whoa, it's equal to 0. I like that. That's amazing. That is actually amazing. Now, if I look at the bottom of the fraction, and I plug in 9 for x, I get 9 minus 9. That also equals 0. So I wind up getting here that the limit is equal to 0 over 0. Well, 0 over 0 is undefined. 0 over 0 is undefined. So I can't just plug it in. And I don't have a nice, beautiful graph to work with like I had before. So what am I going to do? Well, this is where those skills came in. Remember, I made a whole little pre video, I should say, on factoring. So what we're going to do here is we're going to factor the top, and maybe something nice will happen. Well, it turns out that x squared minus 14x plus 45, drumroll please, is going to be equal to, I want two numbers that have an x here and an x there. I want two numbers. I have a plus 45, I have a plus out here and a minus out there. That means these are both going to be negative numbers because they're going to add up to a negative 14 and multiply to a positive 45. And lo and behold, it's going to be 9 and 5. Because 9 times 5 is 45, and 9 plus 5 is 14. I should say negative 9 times negative 5 is positive 45, and negative 9 plus negative 5 is negative 14. And I'm dividing this whole thing by x minus 9. And let's not forget, we have a limit here. We have the limit as sometimes you see that they do this in the limit as a x goes to x goes to 9. So the limit is x goes to 9. Well, this is equal to, it's going to be equal to the, this is going to be equal to the, somehow I'm always getting in the way. the limit now, the x minus 9 on the bottom is going to cancel the x minus 9 on the top. And I just have the limit as x goes to 9 of x minus 5. But there's nothing is good. Now, if I just plug in 9 minus 5, I'm not going to get anything that's undefined. I'm just going to get 4. So I took something here where it was unpluggable, because it would have given me an undefined denominator. But because I was able to cancel and find a common factor, cancel out that common factor, I was able to now to just plug in x equals 9 to the limit, even though x equals 9 is not part of the domain of the function, because it makes the function undefined, I can still plug it in. I can still plug it into the limit to find the limit, and I get 9 minus 5. And let's just take a look here, and we said 4. So let's type that in, and so it's all beautiful. Alrighty, so this is now. I just want to give a caveat. If I would have given you some problem, I'm just making up numbers here now. If I would have given you a problem where I gave you one of these problems to factor, and I factored it, and it came out like this. X minus 3 and I don't know, x minus 5, x minus 9. If the top would have factored like this, x minus 5 and x minus 3, and the bottom was x minus 9, well, I'd be stuck, because I couldn't just plug in x equals 9. What are we going to do about that situation? Funny you should ask. There is an answer. To find a limit like this where we don't have that cancellation, well, let's just get some insight here. Let's look at the our trusty spreadsheet. So we have the x values are 8.9, 8.99, and getting closer and closer to 9 from the negative side. And here it's going 9.1, 9.01, dot, 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 all the way to getting closer and closer to 9 on the positive side. Notice that when that happens, as we get close to 9 in the negative side, it becomes a bigger and bigger and bigger negative number. It's actually heading towards negative infinity. When we come close to 9 on the positive side, then it becomes infinity, positive infinity. So the overall limit here does not exist, and the positive limit, let's try it this way. The positive limit is going to equal infinity, and the negative limit is going to equal negative infinity. And that is the story of that. Actually, let me make this a little more mathy, and let's put in special characters. So I'm just gonna make it a little more mathy. And so it's just gonna be that's much nicer. And that is what happens with that. Now I want to just put this together in a little more official way. So I'm going back to section 2.1. That's right. These are the problems I was looking at. And now I'm just going to click here. This is our textbook section. And I just want to show you some of the official definitions for limits and continuity. I was kind of showing you more of a hands-on way. Now I want to get to some of the official things. So we write the limit as x approaches c of f of x is equal to L, and L will be the limit value. So the limit is as x approaches 5 of f of x is equal to 27 or whatever. So C would be 5 and L would be 27 in the example I just said. And this little arrow means approaches, which is a nice way of saying gets very close to it. And we said that we're looking near but not at the point x equals c. That's the point that I made several times in my discussions. And we did examples similar here. I want to look more at some of the definitions here. And here we have a very nice table here. It is telling me the rule include the function does not have a limit as x approaches 1. And in fact, it looks like the limit is 3 because on this side it's getting closer to 3, and that side is getting closer to 3. So it actually looks like it is 3. That's what it looks like to me. And we want to know when x gets closer and closer to 1. Now, also, if you notice that, again, what we would do is we would factor the top, and the top would be x minus 1 times 2x plus 1. So when we factor it, we cancel out the x minus 1s. Well, if it's 2x plus 1, I can just plug in. I can just plug 1 in. It's just a plain polynomial. I can just plug in the value, and pow, there's my answer. And sometimes we can see by looking at the graph. Sometimes we have a function. Sometimes a formula for the function. Sometimes we have both. A one-sided limit. That's what we were talking about before. A left limit means you're coming in from the negative side, and a right limit means you're coming in from the positive side. And we write it a little C plus right there, or a C minus, over there. So it's the same. Again, I'm just showing you a little bit more of just a sort of a formal way of just saying some of the stuff we say more casually. I personally like to get into the concepts a little more casually, and then look at the formal definitions. At least that's what I wanted to do today. And in our next video, we're going to get to a topic called continuity, but we're going to end this video right now, and I will see you guys next time. It's been absolutely delightful, and we'll see you. Bye.